last lecture, we discussed a Gaussian wave packet and as to how it propagates through empty space. Today, we will rederive Schrodinger equation, discuss the operator representation of momentum and also give a physical interpretation of the wave function, which is due to Max Born. Max Born had given a probabilistic interpretation of the wave function, and we will discuss that today. In one of our earlier lectures, we had given a heuristic derivation of the Schrodinger equation. We started with a wave, a classical plane wave, which we represented as e to the power of I kx minus omega t. In this, we used the wave particle duality, which is given by the de Broglie relation h by lambda. So, this is h cross k, where k is equal to 2 pi by lambda, and then we introduce the Einstein equation that E is equal to h nu is equal to h cross omega, where h cross is defined to be equal to h by 2 pi. So, if I substitute this, we had discussed earlier that this wave function becomes E I by h cross p x minus E t. Then we had said that if we differentiate psi with respect to x and multiply by h cross, so I will get minus h cross delta psi by delta x. This will be equal to minus I h cross times I by h cross. So, h cross cancel out, I times minus I is plus 1. So, this will be just p times the entire wave function psi. So, this will be psi. So, this allowed us to interpret the p operator, p to represent the momentum by its operator minus I h cross delta by delta x. If we differentiate it again, we will obtain minus h cross square delta 2 psi by delta x square. If you differentiate it again, you will get p square by h cross square into I square. So, this will become just p square psi. Then we divided to both sides by 2 m. So, p square by 2 m would represent the kinetic energy of a particle. Then we differentiated psi with respect to time, and if I multiply that differential with I h cross, then we will obtain I h cross delta psi by delta t is equal to I h cross times I is minus 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 plus. So, this will be just E psi. So, we can using this we can represent the energy by the operator I h cross delta by delta t. Now, since we have for a particle E is equal to p square by 2 m plus the potential energy, where V of x is the potential energy function. If we multiply both sides by E by psi, then we get E psi is equal to p square by 2 m times psi plus V psi. But we have shown just now we had these two equations, that E psi was equal to I h cross delta psi by delta t, and p square by 2 m psi is equal to minus h cross square by 2 m delta 2 psi by delta x square. So, I will write this as we had derived earlier, I h cross delta psi by delta t is equal to minus h cross square by 2 m delta 2 psi by delta x square plus v psi. So, this is the one dimensional Schrodinger equation for a particle which is inside a potential field described by the potential energy function V of x. Now, for a 3-dimensional wave, this was one dimensional consideration. For a 3-dimensional wave, we will write psi, the wave function for a classical plane wave, where the vector r represents x, y, z and time. So, I will have a into e to the power of I k vector dot r vector minus omega t. This represents a plane wave propagating in the direction of the k vector. So, now we will define p x is equal to h cross k x and p y is equal to h cross k y and p z is equal to h cross k z. So, instead of the one dimensional formula, we will have psi of, I can write as r t or x y z t. This is a 3-dimensional plane wave. So, this will be a e to the power of I by h cross p x x plus p y y plus p z z, p y y plus p z z minus omega t. If I now apply the same method as we did last time and differentiate first with respect to, so sorry, this will be E. So, this will be E. So, E is equal to h cross omega. So, first with respect to x and multiply by I h cross. So, I will obtain minus I h cross delta psi by delta x is equal to p x times the whole thing. So, this is p x psi. So, I can associate the operator p x with the differential operator minus I h cross delta by delta x. And similarly, if I differentiate it again, I will get minus h cross square delta 2 psi by delta x square is equal to p x square psi. I then differentiate with respect to y. So, instead of p x psi, we will obtain p y psi. So, we will obtain minus I h cross. If I differentiate partially with respect to y, so then we will obtain p y psi. So, now we can associate with the operator p y with p y the differential operator minus I h cross delta by delta y. And I can differentiate it again and I will obtain minus h cross square delta 2 psi by delta y square is equal to p y square times psi. In an exactly similar manner, I can differentiate with respect to z and I will obtain for Pz the operator minus IH cross delta by delta Z. And we will finally obtain that minus H cross square delta 2 psi by delta x square plus delta 2 psi by delta y square plus delta 2 psi by delta z square. So, this will be p x square psi plus p y square psi plus p z square psi. So, you can write down p x square plus p y square plus p z square psi, and therefore, this is equal to p square psi. If I divide both sides by 2 m, where m is the mass of the particle, then I will get p square by 2 psi. So, in the one dimensional equation, we just obtained the first term. In the three dimensional equation, we obtain minus h cross square by 2 m del square psi, where del square psi in the Cartesian system of coordinates is equal to delta 2 psi by delta x square plus delta 2 psi by delta y square plus delta 2 psi by delta z square. If I now differentiate the wave function, if you recall, our wave function was given by psi x y z t was equal to a e to the power of I by h cross p x x plus p y y plus p z z. The easier way to write that is p dot r minus E t. This is my wave function. So, we will have I h cross delta psi by delta t. If I differentiate this, so I times I becomes minus 1, minus minus becomes plus, h cross cancel out. So, you get E psi. And since E psi is equal to p square by 2 is E is equal to p square by 2 m plus v. So, E psi will be so much. So, I will obtain E psi is I h cross delta psi by delta t is equal to p square by 2 m times psi is minus h cross square by 2 m del square psi plus v psi. Now, v here we will assume it to be now a function of x y z psi. This is a very important equation, and this is known as the three-dimensional Schrodinger equation. Three-dimensional time-dependent Schrodinger equation, and a major portion of non-relativistic quantum mechanics is the solution of this equation for different potentials. And we will be discussing the solution for different forms of the potential energy function V of x, y, z. Now, before we give solutions, we would like to obtain a physical interpretation of this wave function, and as I had mentioned earlier, this is due to Max Born. So, I rewrite the Schrodinger equation, and it is I h cross delta psi by delta t is equal to minus h cross square by 2 m del square psi plus V psi. V is the potential energy function which is necessarily real. I take the complex conjugate of the above equation. The complex conjugate of the above equation will be I will be replaced by minus I, H cross, del psi will be replaced by its complex conjugate delta psi star by delta t. This is equal to minus H cross square by 2 m del square psi star V is a real function psi star. What we now do is multiply this equation by psi star, say psi star, we multiply the first equation by psi star and multiply the second equation by psi. And then subtract. If we subtract that, then this term will be psi star V psi and this will be psi V psi star. So, these two terms will cancel out, and if I multiply the first equation by psi star, the second equation by psi and subtract. So, the left hand side becomes I H cross, please see psi star delta psi by delta t plus delta psi star by delta t into psi. This is my left hand side, and the right hand side becomes minus H cross square by 2 m minus H cross square by 2 m psi star del square psi minus psi del square psi star. So, this quantity, as you see, is just delta by delta t of psi star psi. I represent this by a function rho. So, I obtain on the left hand side. So, the left hand side is just equal to I H cross delta rho by delta t. Okay. This is the left hand side, and if I take the minus sign inside, then the right hand side will become, H cross square by 2 m. I take the first term psi del square psi star minus psi star del square psi. Now, the operator del square is actually del square operating on any function, on any scalar psi, is equal to divergence of the gradient of psi. So, I can write this down as H cross square by 2 m divergence of psi grad psi star, this is gradient of psi star, minus psi star gradient of psi, because divergence of a scalar times a vector, this is equal to psi divergence of f plus grad psi dot f. Grad psi is a vector. So, if I take the divergence of this function, first term will be psi divergence of the gradient psi star, then there will be a term which is grad psi dot grad psi star, which will cancel out with this term. So, therefore, you will obtain this. So, the left hand side was equal to I h cross delta rho by delta t. So, I write this down as I h cross delta rho by delta t is equal to so much. So, if I divide by I and h cross, so this will become, the right hand side will become minus I h cross by 2 m into divergence of the quantity without this within the square brackets, and then I will obtain this particular equation. So, on simplification this becomes delta, let me write it carefully, delta rho by delta t. I bring the left hand side, right hand side to the left hand side, plus I h cross by 2 m divergence of psi gradient of psi star minus psi star gradient of psi. This is equal to 0. I define a vector j which is defined to be equal to, please see this, I h cross by 2 m psi gradient psi star minus psi star gradient psi. If I define a vector j given by this equation, then from the Schrodinger equation we are able to derive the equation of continuity. Delta rho by delta t plus divergence of j is equal to 0. This equation, this is a very important equation in any fluid flow. This is given, this is known as the equation of continuity, and I will give a physical explanation in a moment. This is known as the equation of continuity, and therefore, we may assume rho to be proportional to the position probability density. So, we associate rho as the position probability density per unit volume. So, if we interpret psi square d tau as the probability of finding the particle in the volume element d tau, then the particle has to be found somewhere. So, therefore, the integral over the entire space, it is a 3-dimensional integral over the entire space must be equal to 1. This condition is known as the normalization condition, normalization condition. And physically, if you represent a particle like an electron or a proton by a wave function psi, then we will interpret psi square d tau as the probability of finding the particle in the volume element d tau, and since the particle has to be found somewhere, psi should be such that the total integral is 1. The Schrodinger equation is linear So, therefore, if psi is a solution, a multiple of psi is also a solution, and we can choose the multiplicative constant in such a way that this condition is satisfied, where all limits are from minus infinity to plus infinity. Let me for a moment discuss the physics of the equation of continuity. Let us consider a room in which the particles are flowing. So, we inside the room we consider a small volume element, let us suppose dx, dy, dz. So, I have here this length, this axis let us suppose is x axis. So, this length is dx and this length is dy and this is, so x, y and z. So, this is a box. Now, there are particles in the room. Let me try to find out the number of particles that are coming out of this surface, The area of the surface is dy dz and the normal to the area is along the x direction. So, if there is a current density J, which represent number of particles crossing per unit area per unit time, then J dot ds will represent the number of particles crossing the area ds per unit time. So, since S, the ds vector normal to the surface is along the x axis, and this is at the point, let us suppose this is the point x. So, this is the point x plus dx. So, if this area I represent by A, B, C, D, so number of particles coming out per second from the area A, B, C, D is equal to J x evaluated at x plus dx multiplied by the area, and the area is dy dz. Similarly, if this area I represent by E f g h, then the area of this surface is also dy dz. So, the number of particles which are entering this surface, so number of particles entering the area E f g h will be equal to J x at x into dy dz. So, the net outflow from these two surfaces, so the net outflow from the two surfaces will be equal to J x at x plus dx minus J x into dy dz. I multiply the numerator and denominator by dx. So, this quantity becomes delta J x by delta x into the volume element is d tau. So, where d tau, the volume element of the box is equal to dx dy dz. We had considered particles coming out of this surface and particles entering from this surface. Similarly, we will have 4 more surfaces, one perpendicular, 2 perpendicular to the z axis, 2 perpendicular to the y axis. So, we can write that down in exactly similar way. So, the total net outflow from the volume will be equal to delta j x by delta x plus delta j y by delta y plus delta j z by delta z into the volume element d tau. This quantity is known as the divergence of the vector j, and it represents a flow of particles. And since I consider a volume element, if there is a net outflow, then the particle density inside this must be reducing. If there is a net inflow, then the particle density will be increasing. So, divergence of j into d tau must be equal to the minus of delta rho by delta t, where rho is the number of particles per unit volume times rho d tau is the number of particles in the volume d tau. Since this represents a net outflow, so there is a minus sign, from which we get, if there are no sources and sinks in the room, so we get the equation of continuity. So, let me explain this once again, that if I have a closed surface S, then the total number of particles that are going out will be equal to j dot ds integrated over the entire surface, and this will be equal to divergence of j into dv integrated over, this is known as the Gauss's theorem. Another example which will clarify the concept of the divergence is, let us suppose that there is a room which contains a painting. This is a painting on the wall. This is a big painting in the wall, and in this room there is a door here and there is a exit door here, and people are entering this room, looking at the painting and going out. If the number of people entering, there is a constant flow of people. If the number of people entering the door per unit time is the same as the number of people going out, then the population of people inside the room will remain constant. The divergence of the current is 0. So, therefore, delta rho by delta t is 0. On the other hand, if there is a net inflow, that is, if 100 people are entering the room and only 90 people are coming out, then the density of people inside the room will increase. So, there is a net divergence of the current, because of which the population will increase. Conversely, if there are 100 people entering and 110 people leaving, then the population inside the room will go on decreasing. And we are assuming that no person is born or die inside the room. So, there are no sources or sinks. So, whenever there is an outflow, the population density will decrease, and whenever the outflow is negative, that there is a net inflow, then the population density will increase. So, this is represented by the equation of continuity, divergence of j, which is an equation of tremendous importance in fluid dynamics. Divergence of j plus delta rho by delta t is equal to 0. And what we have been able to do is that starting from the Schrodinger equation, that is I h cross delta psi by delta t is equal to minus h cross square by 2 m del square psi plus v psi. Then we took the complex conjugate and subtracted one from the other, and we have been able to derive that delta rho by delta t plus divergence of j is equal to 0. Since this equation represent an equation of continuity, therefore, we physically interpret rho as the position probability density. As you know, rho was we had put equal to psi star psi. So, we physically interpret rho d tau, which is equal to mod psi square d tau, as the probability of the finding the particle in the volume element d tau. And we in this equation, this is a linear equation. If psi is a solution, then a multiple of psi is also a solution, and we choose the multiplication factor such that this integrated over entire space, this is actually a 3-dimensional integral, is 1. And as I had mentioned earlier, this is known as the normalization condition. So, you know, the wave particle duality led us to the Schrodinger equation. We made a heuristic derivation of the Schrodinger equation, and we gave a physical interpretation of the wave function, which was given by Max Born in 1926. He formulated what is now the standard interpretation of the probability density function for psi star psi. For this contribution, he was awarded the 1954 Nobel Prize in Physics, about 30 years after he had made that announcement. Okay. Now, let me give you one example that we had obtained. We had obtained that delta rho by delta t plus divergence of j is equal to 0, where rho is equal to psi star psi or psi square, and j is the current density. So, this is equal to I h cross by 2 m, I h cross by 2 m. Then we will have, just one second, I h cross by 2 m psi grad psi star minus psi star grad psi. Let me consider as a very simple example the plane wave solution. So, the wave function is given by psi is equal to a into e to the power of I by h cross p x minus e t. So, and then psi, so grad psi, this depends only on x. So, if I write down delta psi by delta x, so this will be I p by h cross, I p by h cross times the whole function. So, that is equal to psi. If psi is given by this equation, then psi star, I assume A to be real, but A can be complex also, A into e to the power of minus I by h cross p x minus e t. I am sorry, gradient of psi is a vector. So, this is multiplied by the unit vector. You see, gradient of a scalar function is gradient of psi is equal to delta psi by delta x into x cap plus delta psi by delta y into y cap plus delta psi by delta z into z cap, where x cap, y cap and z cap, as you all know, are the unit vectors along the x, y and z directions respectively. So, this is my gradient of psi, and similarly gradient of psi star will be, let us make A complex. So, A, this is A star. So, if I differentiate this with respect to x, so I get minus I p by h cross. So, minus I p by h cross, and the whole quantity is psi star multiplied by the unit vector in the x direction. So, I have gradient psi this expression, gradient psi star this expression, and of course, I have psi here and psi star here. I just substitute these 4 quantities in this equation. It is a very straightforward substitution, and you will get for j is equal to I h cross by 2 m psi grad psi star. So, therefore, this will be minus I p by h cross psi psi star, that is mod psi square x cap, and the second term will be again the same minus I p by h cross mod psi square x cap. So, that the current density is in the x direction. So, these two terms are equal. I times minus I is 1, h cross cancel out, and there is a factor of 2 coming in, because these two quantities are equal. So, the 2 cancels out, and I will get p by m psi square into x cap. So, momentum by mass is the velocity. So, I get v psi square. So, as you know that if I have a probability, if I have a number density n, and if all the particles are moving in the x direction with velocity v, then the current density is given by this. So, here we have the probability density associated with the particle multiplied by the v. Similarly, I can also, so this is the for a infinitely extended plane wave, which is really a practical impossibility, because it is not normalizable. So, a normalizable wave function is something like a Gaussian wave packet that we had discussed earlier, and we have for the wave function, let us suppose I consider a wave function psi of x, which is equal to pi sigma square raised to the power of 1 by 4 e to the power of minus x square by 2 sigma square e to the power of I by h cross p naught x. This is a Gaussian wave packet which is located around, if you plot the probability function, then it is peaked around x is equal to 0, this is psi square, and whose width is of the order of sigma. So, this is the localization of the particle. The particle is localized within a distance of the order of sigma, and using the formula that I had given you 2-3 turns back, one can show that minus infinity to plus infinity mod psi x whole square dx If I do that, then this will be 1 over under root of pi sigma square, and this will be e to the power of minus x square by sigma square dx, and this integral is obvious. You remember the formula that we had given, and so this will be 1. So, therefore, this factor is such that the wave function is normalized, and so therefore, we can interpret psi of x square dx as the probability of finding the particle between x and x plus dx. And then we write down what is gradient of psi. Psi depends only on the x coordinate. So, I differentiate this with respect to x. So, I get 1 over pi sigma square raised to the power of 1 by 4, etc. And if I differentiate this, I will get minus 2 x by 2 sigma square. So, minus x by sigma square plus I by h cross p naught, and then the whole function. So, therefore, that is psi. I remove this because this factor is contained in psi multiplied by x cap. Similarly, if I take the complex conjugate of this equation, please see, if I take psi star, then this becomes minus, and you will have gradient of psi star. Gradient of psi star will be equal to minus x by sigma square minus I by h cross p naught psi star x. And then I substitute these two expressions in the equation that J is equal to the current density is I h cross by 2 m, and then you have psi grad psi star minus psi star grad psi. If I substitute these two, I leave it as an exercise for you, you will get P 0 by m psi square into x cap. So, this is the velocity, average velocity of the particle, this is the velocity, this is the position probability density, and so therefore, we obtain the expression for the current density. So, from the solution of the Schrodinger equation, we have been able to obtain a physical interpretation of the wave function, and we interpreted psi such that mod psi square d tau represents the probability of finding the particle in the volume element d tau. In the process, we had also obtained an operator representation of p, px, py and pz. So, we found that px can be associated with the operator minus I h cross delta by delta x, and py with the operator minus I h cross delta by delta y, and similarly pz with minus I h cross delta by delta z. This allows us to calculate what is known as the commutator. The commutator between two operators alpha and beta is written as alpha beta within 2 square brackets, and that is defined to be equal to alpha beta minus beta alpha. Alpha beta minus beta alpha. You must have read in the theory of matrices that two matrices may not commute. So, here you have, let us consider that alpha is x and beta is p x. So, I want to calculate the commutator x comma p x operating on any wave function psi. So, this is equal to the operator x p x, the commutator of x p and p x is x times p x minus p x x operating on psi. P x I replace by the operator minus I h cross delta by delta x. So, this is minus I h cross x delta psi by delta x. I have taken minus I h cross outside. So, I will get delta by delta x operating on x psi. If I expand this, then I will get minus x delta psi by delta x minus just psi, because delta x by delta x is 1. So, this term cancels out with this term, minus minus plus. So, this becomes I h cross psi. Since this is valid for any psi, so I obtain the commutation relation x comma p x, x and p x do not commute, and we have this as the commutation relation. So, using the differential operator representation of p x, p y and p z, I have been able to derive x does not commute with p x and the commutator is equal to h cross, I h cross. Similarly, y does not commute with p y, this is equal to h cross, and similarly z does not commute with p z, is equal to I h cross. I leave it as an exercise for you to show that x will commute with y, because x, this is equal to x y minus y x operating on a wave function, and these two are equal. So, x commutes with y, x commutes with z, y commutes with z, and so on. Even x will commute with p y, x commutes with p y, because psi is equal to x p y minus p y x psi. So, this is a differential operator with respect to y, and when I use this differential operator on x, x can be treated as a constant. So, let me write it down carefully. So, this is minus I h cross x delta psi by delta y and minus delta by delta y into x psi. So, since the differentiation is with respect to y, I can take the x outside and then these two terms will cancel out. So, I obtain using the operator representation that x commutes with y is equal to 0, x commutes with z, x commutes with py, similarly y commutes with pz, and so on. The only two quantities which do not commute are x and px, y and py, and z and pz. Px and py also commute, and that follows from the fact that px comma py will be equal to, operating on psi, will be equal to px py minus py px operating on psi, and this will be, both will be equal because delta 2 psi delta x delta y for any well behaved function is equal to delta 2 psi delta y delta x. Because of that, px and py, px and pz, py and pz commute. So, only the three important commutation relations are which the operators which do not commute, and this you all must remember that x px is equal to I h cross, y comma py is also equal to I h cross, and z comma pz is equal to I h cross. And this follows from the differential operator representation of px, py and pz. So, these are the commutation relation because of the differential operator representation of the operators px, py and pz.